Okay, what's up guys? I've decided to make a little video for you guys, especially because some of your tests is coming real soon. So I really hope that this is effective. Okay, now I'm spotting this because this is one of the hardest O-level questions. Yeah, and most of your schools that are setting up their tests will do something very similar, and this is a very difficult concept. Now what you're looking at here is an O-level question. It is not that hard if you are able to slowly interpret what's going on in the question. Okay, so let me break it down for you. So as you can see here, you have a little clarinet player, okay, and what she's doing is she's making some music, okay, and obviously that creates a sound wave. The sound wave travels to this person A, right? Travels to this person at A. So the first question is calculate how many vibrations the reed makes before the sound reaches A. So it's actually not that hard. What you need to do is you need to figure out, okay, what is the period of a vibration? So basically, how long does it take, right, for the sound particles as well as the reed? The reed is just the little end here. How long does it take to make one complete oscillation? Okay. Then after that, you also need to figure out, okay, how long does it take to travel? How long does a sound wave take to travel to A? Then after that, to find the number of vibration, you take the time taken, right, to travel to A. You just divide that by the time for one vibration. Makes sense, right? Because then you can get the number of oscillations or the number of vibrations that the person, or rather the number of vibrations that the reed as well as the air particles inside that they will make before the sound finally reaches A. Okay, so let's figure it out first. First things first, let's go and find the time taken, okay, for what we call one vibration. Okay, or you can call this one oscillation, same exact thing. Okay, so if you think about it, the time taken for one oscillation is also known as your period. Okay, and your period has the following formula: 1 over f, 1 over the frequency. So you just take 1 over 220, and that is the time taken. Okay, very easy. Then now we think, okay, you have the speed being 330 meters per second, and it has to travel a distance of 21 meters. Okay, so if you consider that, right, what's the time taken, right, for the sound wave to travel to A? Very easy. Time taken for sound to reach A will just be 21 meters. You divide by the speed of sound. Super easy, right? 221 over 330. Okay, and this is the time taken to reach A. So finally, what do we need to do? If you want to find the number of vibrations, right? Number of vibrations is just, okay, the time taken in order to reach A, then you just divide by the time for one oscillation. Then you can see how many times it repeats an oscillation. So in other words, right, you're just doing this: 21 over 330, you divide by 1 over 220. Okay, so isn't that just 21 over 330 times 220, right? Because I just flip the fraction here, right? And then I get 21 times 2 over 3, which is just 14. Okay, there are no units here because this is just how many times the particles vibrate. Okay, so should be relatively easy. Now, if you look over at part 2, they say another listener at B, which is right here, okay, is also further from the clarinet, and she hears a sound frequency of the same frequency, 220 Hertz, okay, but with a lower amplitude. So think, if you have the same frequency, right, what is frequency related to for the sound waves? It is related to none other than the pitch, okay, and what is amplitude related to? Amplitude is related to the loudness. So this is something you have to know. It's very easy. Just memorize this portion and it should be quite simple. But look, I want you all to also see the command of the question. So it's very important. So if you take a look here, they want you to use ideas about vibrations of molecules in air. So you need to be very precise in your answer. You need to tackle what changes about the vibration and how does the sound get affected. That is how you are guaranteeing your safety mark for the O-levels. Okay, so let's go and figure that out. So in this case, frequency of 220 Hertz. I want to remind you that frequency here is the number of complete vibrations in 1 second. Okay, so when we say frequency of 220 Hertz, you can just say the particles undergo 220 complete oscillations in 1 second or per second. Okay, that is the meaning of 220 Hertz. Okay, so that's the meaning of 220 Hertz. At the same time, right, look, if the pitch, or rather the frequency at A and B and the reed are all 220 Hertz, then everybody will hear the same pitch. Okay, so now here you can say that since the frequency at A, at the source, okay, and B are all the same, the pitch of the sound wave is the same. So extremely easy question. Just remember, be careful, be precise, and get your A1. Okay, so that's pretty much it. Okay, then I'll do the last portion here also. So amplitude, right, is a little of a tricky one. Okay, I'll define amplitude before we dive into the question here. So amplitude is defined as the maximum displacement of a particle from its rest position. Okay, so think about it. If you have a lower amplitude, okay, a lower amplitude, then you have a maximum, or you have a lower maximum displacement of the air particles or whatever's in the wave, right? Which in this case is air particles from the rest point. Okay, so very easy. So down here you can just write the particles have a lower maximum displacement from its rest position. Okay, and the listener at B, okay, the listener at B hears a sound which is less loud. Okay, so very easy. Just a little comment here. In waves, right, especially when you go over to JC, you'll start to see that amplitude is actually related to your energy. So the higher the amplitude, the higher the energy of the wave. For now, you don't need to know the exact relation. Okay, but once you go to JC, then it's something you're tested on also lah. Okay, quite easy. Okay, we'll move on to this. This is where things get very crazy. Okay, so they show you this. When there is no sound wave going through, the air particles, or rather the molecules in the wall, okay, are all equally spaced out. Okay, now what happens when a sound wave passes through? You start to see these weird things going on. You have many squeezy particles all just going all together, like very close to one another. These are called your regions of compressions. And right beside them, you see that the particles here are spread far apart. This is a rarefaction. Now, why does this even occur? Okay, why does this even occur? So I have to bring you back to the concept of longitudinal waves. Okay, very easy. Now I want all of you all, right, to just go through this little exercise with me. It's a very important concept. If you don't get it right, you will never really understand sound waves. Okay, so let me explain how this is done. First up, we'll draw a little line. Okay, we'll draw a little line, and I want you all to see, imagine if there is no sound wave going through. Okay, wait, give me a sec, a bit OCD. The line is not straight. Okay, is that better? Okay, there we are. Yikes. Okay, so as I was saying, if the line is or rather if there is no sound wave going through, then the particles are equally spaced. Okay, so I'm going to do my best. I'm going to draw 9 particles, okay, that are equally spaced out. Okay, it's not an exact drawing here, so just bear with it. Okay, I don't have a ruler with me right now on this app. Okay, but I'm trying my best to make sure that they are equally spaced out. Okay, and I want to draw 9 particles. You'll see why in a short while I chose 9. Okay, so I have 5 ready. 6, 7, okay, 8, and finally 9. Okay, and now I want y'all to think about it. Okay, imagine if this is, let's say this is the source, meaning that is where the sound is coming from, and I'm telling you, okay, energy is being transferred this way. So you know when there's a source, right, then there's sound energy being passed on, right? I'm telling you the energy is being passed on in this way, and then this is the listener here at let's say at B, like just now, or like at A. It's just a listener to the right, energy is going to the other side. Now the first key concept is that this is a sound wave, right? So I want you guys to all recall what is a sound wave? A sound wave is a longitudinal wave, which means what? Particles vibrate parallel to the direction of propagation of energy, okay, within the wave. Okay, so if you think about it, that means if the energy is going to the right, then the particles must vibrate parallel. So what does that mean for each of these little particles? consider if you consider just one particle like that, okay, the particle will have to vibrate like that and like that. This is parallel to the energy direction. Can you see that? It's all just horizontal. Okay, it's just horizontal in this case. They are vibrating parallel. Okay, very key concept here. Okay, so now that is the reason why they have rarefactions as well as compressions. So I'm just going to erase this, and now I want you all to also draw this with me. Okay, so take some time, you can pause this video or whatever. Okay, just draw this with me. Under particle 1, okay, I want you to draw the y-axis as well as an x-axis. Okay, I want you to draw y and x-axis. Now look, this here is my displacement time graph. Okay, displacement measured in meters, time measured in seconds, put your 0 there. Okay, and you know, a typical wave, okay, a typical wave will look like a sine graph. Okay, so if you all take A math, right, it will look like a sine graph. So let me just draw it out for you all. What I want to do now is I want to draw dotted lines. Okay, hold up. Dotted lines under each particle that I drew previously. Okay, and these dotted lines just extend it all the way down. Okay, if you have a ruler, right, it will be best if you just draw with a ruler, because down here you need to be relatively accurate so you can appreciate the change. Okay, so let me just show you. I'm trying to draw my best. Okay, I don't have a ruler, please forgive me, but if you have one at home, do this with me. Okay, and then look, same thing, going across, down, going across, down. Okay, just down all the way for all 9 of my particles. Okay, and now same thing for the y-axis, which is where your first particle was. Can see? Okay, then now just draw 2 sine waves, 2 perfect sine waves. Okay, so look, I'm going to draw one here, one here, one here, and one here, one here, one here, one here. Ooh, that's a bit off. Okay, and one here. So now look, I'm going to draw 2 sine waves to talk about the displacement and time graph characteristics of my sound wave. Okay, that was a bit off. Okay, so take some time, and please forgive my drawing if it is not 100% smooth. I'm just trying to illustrate a concept to you guys real quick. Okay, so now look, we first have to define where is positive displacement. So you know the particle move left, move right, right? We've just now discussed that. Now, where is considered positive? Okay, you have to know where is considered positive. Okay, for me, I'm going to say, I'm going to define positive is to the right. Okay, I repeat, positive is to the right. Now, I want you to draw what is the position of these particles, okay, when there is a sound wave. So remember, right, the first line that I drew here, this line, is when there was no sound wave yet. Remember, that's why I said there is no sound wave, so that's why they're all equally spread out. Now there is a sound wave, and the sound wave causes the particles to have this displacement distance graph. Sorry, my bad. This is distance, not time. Okay, displacement distance graph. Okay. Okay, and displacement distance, right, shows you the displacement of each particle relative to the distance of the wave. Okay, the displacement time graph is only tracking one particle. So my bad, change this to displacement with meters. Okay, change this to displacement in meters. And so now our job, right, is to draw out these sound particles, okay, when the wave passes through. So I want you all to see, we track our first particle, particle number 1. Okay, look at particle number 1. At particle 1, when the sound wave passes by, what is the displacement? The answer is 0 leh. Which means the particle is at its rest point, right? Because there is 0 displacement. So what do? We draw a little particle here. Okay, we draw a little particle here without any displacement. Okay, without any displacement. So this is how our particle would look like when the sound wave goes through. It's just there. It hasn't moved at all because it is right at its rest position. Okay, now we look at the second particle. Look at particle 2 now. Particle 2 now has maximum positive displacement. Think, we said positive displacement is to the right. So that means the particle, right, will shift to the right. Okay, and I want you all to look. When the particle shifts to the right, okay, it will look like that, right? This is the rest position. Can you see here? Okay, I'll circle. Okay, give me a sec. I've got a little tool I can use. Okay. Okay, look. Perfect, ah. Technology rocks. Okay, look, this here, this position here was the rest position of particle 2, right? This position, this one here. Now, I want to show you that what we have just drawn is this particle, right, has positive displacement now. So that's why we moved it to the right. Okay, that's why we moved it to the right. Okay, and look, now we're going to do 3. Particle 3 was on its rest position, right? Can you see here? It had 0 displacement again. So we draw particle 3 right there. Okay, it didn't move, right? It didn't move. It is still in its rest position. Now let's do particle 4. And look, particle 4 here. Right here, particle 4. Okay, particle 4 here has negative displacement. Negative. Okay, negative means what? Move to the left, right? Okay, if you recall, displacement here is a vector. So we just now defined positive is to the right. So intuitively, right, what would you say? Negative is where? To the left lah. Okay, so that's why for particle 4, it moved to the left. Super easy. Okay, then now look at particle 5. Particle 5 once again, rest position. So I'm just going to draw it here. Rest position. Look at particle 6. Particle 6, positive displacement. So we'll draw here particle 6. Okay, particle 7, where is it? Rest position again. Okay, particle 8, where is it? Okay, sorry, particle 7 rest position. Particle 8, yeah, where is it? Negative displacement, right? So it's here. Okay, I'm just following. I'm at this guy now, which is here. Okay, this is the one that I was doing. Okay, and then finally we reach the last particle, particle 9. Particle 9 is where? Particle 9 is right here at its rest position again. Okay, this is why you can see for only longitudinal waves, right, there will be regions of compressions, and rarefactions. Okay, so we have just proven this out. Now, very important concept. Okay, very important concept. You must know why there are even regions of rarefactions and compressions. And more importantly, I want you all to see one trend, because they've always tested this in O levels. Look, what is one wavelength? I hope you all agree with me, right? One wavelength is this distance. It's like the length of one sine curve, right? Okay, or you can consider it from peak to peak. This is also one wavelength. So I can label this as one wavelength or one wavelength also. Okay, below. So either one of these. Or you can even call it, some of your schools will also write, okay, it's the distance between two consecutive truths. Okay, which is right here also. Right, you can see that? Okay, and so let's look at this. How does that look like on the graph? Okay, if I consider this now, okay, let's say I choose this point. The length from here to here. Do you all see, right? It is actually the distance from rarefaction to the next rarefaction. Okay, likewise, if I go and choose this particular to this particular one, okay, that one is not very meaningful. Okay, it will be this distance also. You can also mark this out as one wavelength. Okay, and at the same time, look, you can also say that this is one wavelength. Okay, I want to show you all this. Okay, I'll highlight in blue because it's getting a bit messy. Okay, but this is also one wavelength, right? This is also one wavelength. Yeah, like that. Because can you see I'm doing an upside down sine curve, right? That's one wavelength, right? Can see there, for one wavelength, it is actually the distance from compression to compression again. Okay, from compression to compression again. So very important, you must know. For the wavelength of a sound wave or a longitudinal wave, it is from compression to the subsequent compression. Okay, likewise, you can also say it's the rarefaction to the subsequent rarefaction. Okay, this is a very crucial part. Okay, later we'll be doing a question just like that. Okay, so now I'm just going to clear my diagram here a bit because of, well, I want to show you all a very important part. Okay, that will help us solve the next portion of the question. Okay, so what is the important part? Let me just show you now. Give me a sec. Okay, I need to delete all of this. Okay, let me get rid of this mess. Okay, just bear with me, almost done. Okay, I want you all to see what happens when half a period passes by. Okay, when half a period passes by. So think, if half a period now passes by, okay, let's think in one period, okay, we can say that the wave will move one wavelength. Correct? Easy, right? Think about it. In one period, you will move one wavelength ahead. So then, what about half a period? Okay, what about half a period? So this is a very crucial question. It came out in O levels. I'm showing you is actually the answer to the next question. In half a period, your wave will move half a wavelength. Correct? Your wave will move half a wavelength. Now, draw this out with me also. So, I'm going to draw it on my red line. When I'm moving half a wavelength forward, can you imagine this point A, right? This point A will now move half a wavelength here. So this is its new position. I'll call it A prime for now. So the whole graph, right, technically just shift to the right by half a period. Okay, by half a period. So it moves by half a wavelength in half a period. So I'm going to erase this and I'm going to draw in red my new graph half a period later. Okay, so eyes here, it will just, it will just look something like this. Okay, wait, hold up. Okay, and it will look like that. Do you all agree? Very easy, right? You just move half a wavelength forward, right? Can you see this is moving half a wavelength? Okay, so now when it's half a wavelength, look, I'm going to plot out the new graph. I'm going to plot out the new graph of the particles. Okay, so I'm going to I did the same thing just now, right? I'm going to consider now, but only for the red line. So look at my red line now. First particle, original, same. It's at its displacement, right? It's at 0 displacement, so it's at its rest point here. Okay, this is the new one I'm drawing corresponding to the red line. Look at particle 2. Okay, it's here, negative displacement. So if it's negative displacement, it moved to the left. Right, it moved to the left. Then particle 3, look, 0 displacement here, right? So then we can say, ta-da, it's right here. Look at particle 4, positive rightward displacement, so it moved here. Okay, look at particle 5, it's at its rest position. Okay, 0 displacement, so we'll draw it here. Particle 6, look, negative displacement, right? So it's moving left. Okay, then now particle 7, same, rest position. You can see particle 7 is here, so rest position. Particle 8 move to the right, positive displacement. And now finally let's look at particle 9. Where is it? Same thing, rest position, right here. Easy, easy, super easy. Now, look at something magical that just happened. Okay, previously, right, this was half a period. Correct? Remember I told you all, we are just considering what happens half a period later. Half a period later, look, all my rarefactions, right, this rarefaction has now become a compression. Correct? Now look at my original compressions. What have they become now? They've become rarefactions. Correct? So see, compression turn into rarefaction, rarefaction turn into a compression, and a compression again. Okay? So very, very simple concept. Every half a period later, your compressions turn into rarefactions. Your rarefactions turn into compressions. Super duper duper easy. Very important. Okay, tested how many times? Many, many times. Okay, that's why I want to go through this now because I have a very, very strong gut feel okay, that is probably going to come out. Okay, so look over at this. Now, this is the same question from before, right? It's the same worksheet, just refreshing your brain. Okay, then look. On line Y, okay, in the figure, mark a distance equal to 1 wavelength. So we've already done that previously, right? Just now I showed you all. Ooh, thanks. Okay, never mind. You know what? I'll erase this. Okay. Okay, for 1 wavelength, what is the distance? The distance is just from compression to the next compression, right? Or rarefaction to the next rarefaction. So I'll give you 2 of the answers. This is the center of your compression. This is the center of compression. So you will just mark out this distance, call it your wavelength, like that. So easy, right? Then next, this is your rarefaction, this is your rarefaction, right? The center of the rarefaction, where the particles are the furthest. Then what do? Just draw 1 wavelength again. Life is good. Okay, very easy. That's it. That's the answer for 1. Done. Now, the next one they ask you, okay, explain how sound energy is transferred. This one is my favorite. So many people die at this stupid question. Hey, you cannot die. You are my A1 student. You cannot die. Okay, so let's look at this. How does sound energy get transferred without the transfer of matter? So perfect. This is actually talking about a wave motion. Okay, so you think about it. How does energy transfer? So the energy transfers when the particle hit the next particle, passing on energy. Okay, so very crucial concept. The only way that energy is being passed on in a sound wave is when particles collide with neighboring particles, passing on energy. So you can say that at the disturbance, or rather at the source of the wave, okay, which is where the disturbance occurs, right, producing the sound wave. Okay, particles vibrate and collide with neighboring particles. Okay, transferring energy upon each collision. Okay, so every time they collide, they pass on energy. Okay, that's how the sound wave passes energy through. Okay, so very simple concept. We've tackled the first mark, how energy is being transferred through the wall. So you can say that particles in the wall, okay, undergo collisions, okay, undergo subsequent collisions, passing energy from one end to another. Okay, and now just to be safe, every time you talk about sound waves, right, just find a way to squeeze in the concept of rarefactions and compressions. Okay, then you can say creating a series of alternating regions of compressions and rarefactions. So this is always one thing in the prelims, right? You will always see a lot of answer keys trying to force you to write out some way or another alternating regions of compressions and rarefactions. So if you encounter sound wave questions, right, for me, I would rather write a bit more, okay, and then try to squeeze in as much keywords as I can to get the mark. Okay, but I'm telling you now, the main point of this question is just the collision and hence the transfer of energy. The second mark, how do you get it? How come there is no transfer of matter? This is for all waves. So you have to write this down. Okay, since the particles, okay, vibrate about a fixed position, okay, there is no net transfer of matter. Okay, so this is the second mark. So if you think about it, right, what I'm trying to say is, look, consider one particle, okay, any of these particles. Let's just imagine one of these particles. How do the particles move? Okay, let's imagine this was before the sound wave came. Now the sound wave come, the particle on its left, right, hit this guy. Okay, so let's say particle B hits particle A. What happens? Particle A will now be forced to move to the right, right? Right? Then after that, particle A will hit another particle, let's call this particle C, and then it will bounce back. Make sense? So then what happens is particle A goes to the right, hits C, comes back. Then it will go back to the left, hit the other particle, and come back. Doesn't this obviously show you, oh, so actually, I'm hitting left and right, but there is a fixed center. This is my fixed position. Okay, in other words, sometimes your books will call this the equilibrium position. So this is my center of my vibration. So if all particles, right, vibrate about a fixed point, then obviously the matter from the left don't go to the right. That's just logical. I hope you all can visualize that. Very simple. Okay, so that's it. Now we look over at this. Describe how the figure above shows that the sound is a longitudinal wave. Now, this is very easy. Okay, remember, all longitudinal waves will cause the particles to vibrate left and right. Okay, not left and right. Okay, let me be more specific. All longitudinal waves will cause your particles to vibrate in the same direction as the energy propagation. So if energy is going to the right, then these particles vibrate left and right. Okay, if energy is going up, then how? The particles vibrate up and down. Okay, is the key idea is parallel to the direction of propagation. And this creates what? This creates what we call a longitudinal wave, where there are rarefactions and compressions. So the moment you show there is compressions and rarefactions, instantly you know the particles are moving in the same parallel direction to energy transfer. Hence, it must be a longitudinal wave. Okay, so think about the concept, take some time, process it. The way that you solve this and answer this question is you can just say that the wave in the figure above has alternating regions of compressions and rarefactions. Okay, and thus, okay, when they have alternating regions of compressions, rarefactions, compressions, rarefactions, thus it is obvious that particles vibrate in a direction parallel, okay, to the direction of energy propagation. Hence, by definition, it is a longitudinal wave. Longitudinal. Okay, very simple concept. That's pretty much it. Yes, I hope this was rather insightful for you all. Now look over here, the last part. One complete oscillation is T. Okay, so they ask you, okay, what happens if the time taken for one period is T, capital T. Now they want you to show what happens to what happens when half a period passes on. where are my compressions now? So remember, right, just now I showed you all this diagram here. After half a period, what happens? All my compressions turn to rarefactions. All my rarefactions turn to compressions. So you go back here. Okay, we look back up. So all my compressions turn into rarefactions, my rarefactions turn into compressions. So they want half a period later, right? So this is the new compression. This is the new compression. Because they were originally rarefactions, half a period later they'll turn into compressions. Okay, I'm just gonna neaten my answer out here and here. Okay, very easy, super duper easy. Okay, so I hope this was simple for you guys. Now I'll do. Okay, I just got 3 more questions only. Okay, just bear with me. Question 3 here. Sound wave is sound is propagated in the air above, and now they want you to just draw a little diagram. So this is a very simple practice question. Okay, a sound wave of wavelength equal to AB is sent through the air in the direction of PQ. So look, this is the distance AB, and this is one wavelength. Okay, this is one wavelength. Okay, so first thing they ask you, sketch the possible positions of particles 1 to 9. Very easy. Listen, don't do this first. Don't do this first. Okay, you should always draw. You should strive to always draw your displacement distance graph first. Then you plot, right? So if you remember what I did here, did I just start drawing the particles first? No, right? I went to draw the displacement distance graph. So it makes my life so much easier. Same thing here, lor. Okay, so you look at part 2. Sketch a graph of how displacement varies along PQ. Super easy. Now look, you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, you have 8 sections technically between A and B. So now I'm going to plot in the middle here. This is where I would have 0 displacement. Now I'll show you why. I want to draw a perfectly nice wave that goes like that. Correct? I want to draw a perfectly nice wave. Yeah, I'll show you with the disappearing too. I want to draw a wave that goes like that. Can see that? I want to draw something that goes like that. That's what I want to draw. Okay, so that's exactly why I'm trying to plot it slowly. Okay, so you know that it reaches here. Okay, for me, let me try to draw it out at the max. Okay, and then same thing for the middle particle, it will go there. Okay, so just draw this little graph out. Take some time, make it neat. Okay, and then, yikes. Okay, and then should be quite simple. Okay. Yikes. Okay. And once you reach this is how your graph looks like. Super easy. Okay, now I'm going to clear this off so I can draw. Yikes. Okay, wait, hold up. Man, I need to do it one by one. Okay, give me a sec. Okay, and then yeah, that's it. Okay, then now look, they want you to go and sketch a graph of the displacement, okay, along the positions here, and then look, they want you to say, okay, take direction. Okay, I'll highlight it. Take direction to the right as positive. Means if I have positive displacement, it is to the right. Okay, if I have positive displacement, it's to the right. Okay, so then now after that they want you to draw the positions of the particles on this line here. Can you see this line? You need to draw the new positions. So easy game. We've done this so many times already. Now look at 2. Okay, where does it correspond to? It corresponds to almost the highest displacement. So there's still a particle 3 with slightly higher displacement. So what I'll do now is I'll just draw particle 2 quite far to the right. So I'll draw it somewhere in the middle. Okay, and so this is particle 2. Can you see? It's somewhere to the right. Okay, it's like here. Okay, and now what about particle 3? Particle 3 is supposed to have highest displacement. So if you consider this is the displacement for 2, displacement of 3, right, must be slightly more. Okay, so that's exactly what I'm going to do now. I'm going to draw that it's slightly further than 2 from its rest position. So this is 3. Can you see 2, right, is just a bit off, it's like halfway. 3 I'm trying to draw is further off from its rest position. Okay, I hope that was clear, very, very simple. Now look at 4. Okay, look at 4. Particle 4 is corresponding here, right? Same thing, it still has high positive displacement. Positive still, can you see it's positive displacement? Right, this is more than 0, so it's positive. So it's still moving to the right. Okay, but it's not as far as 3 was from its rest position. So if you look at 4, where will 4 be now? 4 will be like the same as 2. Can you all see? It is this distance. This distance is approximately the same. Okay, D and D. Okay, you can see that? So yeah, that is particle 4 law. Very easy, super easy. Now, we look at 5. 5 is drastic, right? Look, 5 is at its rest position. Super easy. So, you just draw 5 here. This is the easiest one. Then now 6. Interesting question really. Look, 6 here is now negative displacement. Quite high negative displacement. So, instead of drawing it to the right now, you draw to the left lor. You draw in the middle. Can see? This is 6. Okay, 7. Maximum displacement to the left. Okay, so this is 7. Can see maximum negative displacement. Very high negative displacement. Then we look at 8. Where is 8? 8 is also pretty high displacement. That will be here in the middle, somewhere there. And then finally 9. 9 is right there. Okay, 0 displacement. Can see? 0, 0. Perfect. That's it. Okay, and they've technically drawn particle 9 for you. So you don't really need to draw 9. Okay, you can see even if I erase my 9, it's already drawn for you. Okay, so you don't need to draw, but this is it. This is particles 1 through to 8. Okay, so done. Very easy. Now we do the last one. A sound wave can be described as a repeated sequence in the change of pressure. So we think, where is the highest point here, or where is the highest pressure point? Intuitively, look, down here is a rarefaction. Particles are far from one another. Here is a compression. Particles are very close together. And I hope you all can see right on the screen. 5 is the center of the 5 is the center, the definite center of the compression. So at 5, right, that is where it will be the most squeezy. If you think about the other topic, kinetic model of matter, that region there, particles are all squeezed in together. So there is the highest number of molecules per unit volume and per unit area, right? So if they all randomly hit each other and they're so concentrated there, I hope you all agree, there is the highest number of frequency of collisions per unit area, which means intuitively it has the highest pressure. So that's how you explain it. So you can say, okay, my H on figure B, okay, is where my pressure is the highest. Okay, so that's it. Super easy, very standard. Okay, and so my answer will be written out like that. Okay. On figure B, identify. Okay, I'm done with H already. Now I just need to explain. Okay, so you can say that H is a position where, okay, a position of H is the center of the region of compression. Okay, at this region, particles are closely packed together, and thus the frequency of collision is highest here. Okay, thus average force per unit area is highest here, and pressure is highest here. Okay, so that's the answer. Super easy. Okay, I hope this was clear for you all. So 1, 2, and 3, done. Okay, we're done with enough of the sound questions. Now let's look over at light. Okay, light, simple, think. Down here, right, first of all, this is a diverging lens. Okay, so I've told you all before, diverging lens rarely come out, but you still must be prepared for prelims as well as your other school tests. In O-level, it's very unlikely that they'll test this out. In fact, if you check the learning syllabus, right, syllabus outcome, they don't expect you to know diverging lens like very in-depth. Like, you can go and check the syllabus outcome. Diverging lens is just a small subsection. Converging lens is the main tested one. Diverging lens, right, if you think, it looks like this. Okay, wait, let me draw it out. Your diverging lenses look like that. So if I shoot a perpendicular ray like that, what this does is it spreads it out. Okay, it throws it out. So imagine if, okay, I'll draw a little diagram for you. Okay, if it goes through the direct center, it shouldn't be deflected. Okay, if it goes through the sides here, then it'll go out like that. Go through here, it'll go out like that. This is called diverging. Okay, you have learned converging before. Converging is like that. Okay, if you shoot rays, parallel rays, it will just go straight through. This one will cut down at F, and this one will also cut down at F. Now, the same concept actually applies for diverging. You see, if you trace back where it cuts the principal axis, this is the F. Okay, this is the F. Okay, on the left hand side. So yes, it spreads out, but if you trace back the virtual rays here, they are F. Okay, that is where it intersects the focal point. Okay, So now we look over at how to solve the diagram. Okay, how to solve this question. Okay, going up, look eyes here, standard. Okay, I'll draw with a straight line to make it even better. Now we look at this question. You see, right, down here is a diverging lens, right? Remember I told you to go out, but we don't know how it goes out, right? We are not too sure, right? Then remember I said if you extend back, it must cut F. Correct? I said if you extend back, it must cut F, right? So actually the trick here is you measure from F, then you go out like that. Okay, and this is how it should look like. Just like this. This is your ray. Now look, is this ray section here? Is this ray section, the one I'm highlighting now? Is this real or virtual? The answer is virtual. It is 100% virtual. So what must we do? We must make sure it's a dotted line. Okay, so I'm cheating. I don't have a dotted line function on this app, sadly. So I'm using a white marker. Okay, but I hope you all have at home. Just draw a dotted line. Okay, with your pencil and eraser. Okay, I'm drawing a dotted line to represent this. Okay, so I hope this is clear. This is the first ray. Second ray is undeflected, right? So super easy. Okay, can you see it cuts through the center? Same concept. It's not deflected. Now, if you consider this, look, the rays here, right? They intersected where? They intersected. Okay, can you see it came from the top, right? The rays came from the top of the object. This one caused it to diverge out. This one just went straight through the center, so it's undeflected. But they both came from the top of the object. So I want you to see that the image, right, is formed where these two rays that came from the top of the object met, and they met at this position. Now, where's the image? It's here lah. Okay, the image is here. Okay, the image is here. Okay, and it is definitely 100% virtual. Why is it virtual? Easy, right? You can tell, right? Look, can you see this line from here? I draw the dotted line for a reason. It's a virtual ray. So obviously it is going to be a virtual image lah. If you have a virtual ray, obviously you have a virtual image. Okay, it's not one that can be projected on the screen. These are extrapolated rays. They are not real rays. Okay, you just extrapolate backwards. They are not real rays. Hence, it cannot actually be projected on the screen. Okay, that's the meaning. Virtual means cannot be, okay, image cannot be projected on a screen. Okay, so super duper easy. I hope that was clear for you all. Now, we look over at the last one here. Okay, so this is the other ray, right? Very hard. Oh, this is the other ray, right? A lot of people always die at this. They say, how the hell do I actually draw this bottom ray after it passes through the diverging lens? It won't cut through F, right? It won't cut through F. It won't cut through F because this is not a converging lens. That's one. Number two is, look, the ray is not even perpendicular to the axis. It will not bend to the focal point. So how does it actually bend? Okay, and then this is where you must think a bit. Look, it came from the bottom of the object. Okay, a light ray came from the bottom of the object. Where must it correspond to? Any light ray, right, that comes from the bottom of the object must look very similar to the bottom of the image. Right, if you consider any lens, okay, you consider any lens. Imagine this is my specs here, and let's say I look at an elephant, okay, and I see the elephant's face. Where does the light ray come from? Does it come from the elephant's body, the trunk? No, right? It came from the elephant's face also. So it's the same concept, right? If your light ray comes from your object's bottom, it must end up and it must match with the image bottom. So we found our image now. Now, how do we find the ray that passes through, okay, so that it meets at the bottom of the image? We draw from the bottom of the image here. So you can see, right, from the bottom of the image, I'm just drawing a line extending down. Okay, because look, bottom here of the object must correspond to bottom of image. That's it. That's literally it. Okay, so once you're done with that, look, just draw your ray. And remember, this is called a virtual ray, right? Because it's a virtual image. So this, please shade it also. Okay, now we look at this option. Okay, which of the following diagrams look just like this? Okay, the answer is A. Can you all see? The bottom of the object corresponds to the bottom of the image, and likewise, the ray is actually the diverging outwards, and it meets back at F. Okay, very simple, right? So the answer is A. Wow, white pen looks nice, huh? Okay, now let me move on to the last question for the day. Okay, so this is a revision. Please do your best, get an A, and then full send. Make sure you do it right. Okay, here, this is my object. They want you to complete this diagram. So I hope you all still remember there are 6 cases for light. Go and memorize all 6 of them. I have a very, very strong feeling it will be case 1. This is case 1, by the way, where you have a virtual ray, okay, when you put an object between the optical center and F, when you put it along this region. Okay, between optical center and F. Now, how do we solve this? So first things first, you need to know 2 rays. Very easy, First ray is you draw a perpendicular line like that. And where must this perpendicular line cut? All of y'all know. Super easy stuff. Okay, you just draw your ray from there, cutting the focal length, focal point. That's it. Okay, this is the first ray. Very easy. Then what do we do next? Okay, what we do next is we draw our second ray. From the top of the object again, cutting through where? The center lah. Easy game. Now, basic intuition will tell you something here. Will these two rays ever intersect on the right? The answer is no. Okay, it won't intersect on the right. So where will they intersect? They will intersect on the left, meaning there is no image formed on the right. Okay, so the light rays don't meet, right? There is no image formed on the right. There is no real image. Okay, so where is the image formed then? The image is formed when you extrapolate it backwards. So what I want you all to do, okay, for me, look, I have to extend this line because I don't have a ruler and a dotted line. You just draw backwards. You extend these 2 lines backwards. Ooh, yikes. Okay, you just draw backwards like that. So you can see mine is drawing backwards. That's it. Super easy. Okay, and then now here's the job. Here's a very, very important thing you need to do. These are extrapolated virtual rays. Okay, they are not real. So dot it. Crucial. Okay, crucial. Just like that. Okay, and then also dot these rays lah. Okay, and now I hope it's very clear lah. Y'all can see also where it intersects, right? Where it intersects, that is where your image is formed. And this is none other than a virtual image. So look, they intersect here. I draw my image here. Okay, let me draw it with black lah. Bit weird to draw it otherwise. Okay. Okay, so this is my image here. Very easy. Okay, and now remember virtual image, virtual rays. So everything dotted for the virtual rays and the virtual image. So you can see I'm dotting my image as well. Okay, too much dots. Okay, and I'll call this just here my image. Okay, now finally we reach the last section. Okay, the last section here. They ask you, A, complete ray P. How? Ray P, what the, right? Ray P is here. It came from the bottom of the object. So I hope you all grew a bit wiser from the last practice that we had. So think, if it came from ray P, right? At the bottom, the ray P comes from the bottom of the object. Where must it correspond to? The bottom of the image. Okay, so this is the bottom of the image. Just drawing straight line through across again. And this is how you complete the diagram. Okay, so finally, once again, this image here is virtual, so you have to dot these lines. Okay, you have to dot these lines. And your answer should look just like this. Okay, your answer should look just like this. Okay, so you can say that this is ray P. Okay, that's how you tell how it bends through the converging lens. Okay, now finally, last part of the day, they say this. Okay, will the image still be produced? Okay, state the effect if it is still produced. So first question you need to ask is an implicit question is the image still formed if I cut off the bottom half of the lens? Okay, if I cut off the bottom half of the lens, the answer is a resounding yes. Okay, I repeat, the answer is a resounding yes. So I'm going to draw out and prove to y'all if I cut the bottom of the, if I cut the bottom here, look if I cut out the whole bottom, okay, I erase the bottom, I destroy the bottom half of the lens. Do y'all see here, right? My rays are still shooting out and they can form back, correct? My rays can form back, right? If my rays can form back, then my image is still formed lah. Right? My image is still formed. So the answer here is, here you must write. Okay, actually you know what? Let me just undo this. Okay, then the answer here, okay, for this portion will be the image will still be formed. by the top half of the lens. Okay, but is there any change to the image? Let's think. The size never changed, right? Because just now you all saw when I raise the bottom half, it still intersects at the same point. So the height of the image is still the same. Correct? It's still the same. Think so does anything else change about it? So remember, whenever we describe the characteristics of image, we have LOST. L stands for the location of the image. O stands for the orientation. That means is it upright or inverted? S stands for the size. How big? Is it bigger, smaller, or the same size? And T stands for the type, whether it's real or virtual. Okay, so did anything change of this four? Let's think. Did the location change? No. Did the orientation change? No, it's still upright. Did the size change? No, it is still intersecting at that point. And did the type change? No, it is still virtual. So your answer is none of these changes. Okay, but something else does change. And so this is a very tricky, very, very difficult question. You need to think about it from the light perspective. You all see here, right, that your bottom ray or your bottom half of the lens is actually going to create a bright image. Consider why. Why is it going to create a bright image? Because more light rays are refracted back. Okay, are refracted back to form the image. So if I cut off the bottom half, right, all the light rays are going to the bottom half, okay, which is here, which is what I've just highlighted. All of them going to the bottom half. They won't be refracted back to the image. Okay, they won't be refracted back. So for example, you see this, it won't form already. It won't be refracted back already. Okay, so then the answer for this section, once again, is the image. Okay, the image will be less bright. Okay, and how do you explain that? Okay, however, since less light is refracted from the bottom half of the lens to form the image, okay, then the image will be dimmer. Okay, or you can write less bright. Okay, and honestly quite a simple concept lah. Okay, so I hope this was very, very clear for you all. Very, very important little lesson here for you guys. Now just to let you know, okay, this is a standard question. Okay, standard question, it can always come out in very difficult prelim papers. So I need you all to remember one thing. Even if they cut the top half like that, like what we did before, you can still form an image. Okay, you can still form an image. So no matter what, the image will be formed if you only cut off one half of the lens. Okay, because if you cut off the top half of the lens, the image will be formed by the bottom, but the result is always the same. There is now less light. Okay, I repeat, there is now less light. So if there's less light, then the image is dimmer. That's the answer. Okay, so super easy. Look, I hope that some of this comes out in your test upcoming soon. I wish you all the best, dear full sender. No A, no talk. Okay, go and do your best. Okay, see you guys. Ciao.